In pre-calculus, I'm going to be going through section 1.7. And in 1.7, sometimes it's not everybody's favorite because we're talking about word problems here. We're modeling with functions. But you're going to find, again, that a lot of this is formulas you've already seen before. And if you don't remember the formulas, remember you can go into the Appendix B and get some of those. So we will be able to, and this is from your yellow objective sheet as well, we want to write functions from formulas, graphs, verbal descriptions, and data. So we have a lot of different types of problems that we're going to take a peek at, and some are kind of a mix and match of those topics. So we have forming functions from formulas, which is one of the things we've already been working on. And it says, write the area A of a circle as a function of its, and then in A it's the radius. And I realized, well, that's already what we do because the area would be pi r squared. Now, how we let people know that this is area in terms of the radius is with our function notation right here. Area in terms of the radius. Now for B it says, let's change this up and let's do this in terms of the diameter d. So what I have to do is think about the fact that I used the radius before, and that the radius is half of the diameter, or the diameter divided by 2. So this time, the area will be found in terms of d, and it will be pi times d over 2 squared. And what we would do is we would square both the numerator and the denominator, because when you have pure multiplication or division inside parentheses, you can go ahead and distribute that power of 2. So that will be d squared over 4, and putting it all together, it might look a little nicer if we have pi d squared over 4. So that's area in terms of diameter. So what we're doing here is we're building these formulas for whatever math we would need to do. This formula would be best if somebody handed you a sheet that said, these are the radii of multiple circles, and we want you to find the area of all of them. And then if they changed that sheet and gave you the diameter, well then you'd want to use this formula for a whole sheet of problems to figure out what the area is. And in this last one it says, now we're going to give you the circumference. So I think, all right, circumference equals 2 pi r. So if I can get r by itself, then I would have c, and I could put that back into my area formula. So if I divide both sides by 2 pi, r equals c over 2 pi. And now I go back to my red formula, and I substitute r with c over 2 pi. So the area in terms of c will be pi times c over 2 pi, the quantity squared. So that will give me pi times c squared over 4 pi squared. And then I can do a little reducing here. So I can cancel out one of the pi's, and I will have c squared over 4 pi. And that would be the area in terms of the circumference. So formulas can be manipulated. That's what this is all about. If we can manipulate the formula to our advantage, that's what we want to do. And this study is called literal equations. So we're making our literal equations so that they're more useful for what we're going to do. Now, this next one is a maximum value problem, and hopefully when I said that, immediately you said, oh, wait a second, I think I remember doing those in Algebra 2 because we did. And they were exactly the same type of setup. So a square of side x inches is cut out of each corner of an 8 by 15 piece of cardboard. So this was 15 inches from top to bottom, and this was 8. But we wanted to fold this up and make a box. Doing that meant all of those little corners that get moved up, pushed up, those are going to have x as their side length. So we're making this open top box right here. And we have to figure out what the dimensions of that would be. For A, it says write the volume V of the box as a function of x, which I already used x in the drawing, so that makes perfect sense. So the volume in terms of x will equal Well, volume of a box is length times width times height. If we fold this up, x is going to be the height. It did have length and width of 15 and 8, but we have to subtract 2x from both of those because we're cutting those corners out to fold this box up. Now, I need to keep going because, as you can see, there's a lot more questions I have to answer about this. So what I would do is do FOIL, and that would give me 120 minus 30x minus 16x plus 4x squared, and then multiply. Actually, I probably would simplify first and put those two middle terms together and also put that in standard form with the x squared term first, because that would drive me bonkers not to have that in standard form. So x times the quantity 4x squared minus 46x plus 120, and finally distribute the x, and I ran out of room, so I'm going to go up here. And that will give us 4x cubed minus 46x squared plus 120x. And they have some questions for us here based on that information. So for part B, it says find the domain of V as a function of x. And it says note that the model imposes restrictions on x. Now, obviously, we have to start with 0. So we know that our domain is definitely going to start with 0. We'll put domain of V, 0. Some would argue that that should be parentheses because we wouldn't have a box if that dimension was 0. And you would argue that rightfully so. But this book sticks with the fact that we start with 0. Now, what about the other dimensions? Well, here's what I know. I know that 15 minus 2x has to be greater than or equal to 0, because if it's not, then we're using a side length that's negative, and that doesn't make any sense. So we'd subtract 15 from both sides and divide by a negative 2, which of course flips the sign. And 15 divided by 2 is 7.5. And word problems are one of those times when we can use decimals. It's acceptable to use decimals in word problems because oftentimes that's how people think of it. When they go to buy a piece of lumber, 7.5 feet, 7.5 feet, they don't think of it as 15 halves. And then the other side length was 8 minus 2x. And that also has to be greater than or equal to 0. So we go through the same thing. We're going to move the 8 over by subtracting, and then we're going to divide by negative 2. And we find out, well, it has to be even less than 7.5. It has to be less than or equal to 4. So in order to keep all of our dimensions positive here, our domain has to be from 0 to 4, including the 4. And again, use interval notation. We've talked about how there are very, very few times when it's actually simpler to write something in our other formats than interval notation. So keep using interval notation whenever possible. All right, then C. Graph V as a function of x over the domain that you just found in part B from 0 to 4, and use the maximum finder of your grapher to determine the maximum volume that such a box can hold. Okay. So we need to get into the graphing calculator and we need to put in our cubic formula. Y equals, and we have 4x cubed. Pop it out of the exponent there, minus 46x squared plus 120x. I'm just double checking real quick that that's punched in right. And then for my window, I know that I have to stick with 0 to 4, and not quite sure what I should use for the maximum volume. So I think, well, what if it were 15 and 8 and 1? Well, then that would be 120. So I'll use 0 to 120, just trying to think of the biggest numbers possible with an easy solution, and hit graph. And it works. I can see where the maximum is. And what's even better is Blinky, our hypoallergenic pet, can find it. Blinky the cursor. Number 4. So we will go to the left side of the hill and press enter. Then back back to the right side of the hill and press enter and hit enter through guess. And there it is, 1.6666, so we'll round it to 1.667, and our maximum volume is 90.741. So go back, and I'm going to write down what our ordered pair was. It was 1.667, 90.741, so we don't forget. But this problem specifically asked the maximum volume. So that volume is 90.741, and this was in inches, so cubic inches. And then D says, how big should the cutout squares be in order to produce that box of maximum volume? And that's what we found with our X. So it's approximately 1 2/3, or you could say approximately 1.667. On the machines, they're probably going to use 1.667 and try to get as close as they possibly can. And that is inches. So there's another one. I mean, we definitely were using a formula, and it was our volume equals length times width times height. But it also could be argued that that meant right functions from verbal descriptions, which was another part of our objective. So either one of those. And it is something that we did study in Algebra 2. So those should feel like memories as we go through that problem. This one says forming functions from graphs. So that's another part of our objectives. We are going to protect an antenna. A small satellite dish is packaged with a cardboard cylinder for protection. You can see the cardboard cylinder inside here. They don't want that box pushing down into the working parts. So the parabolic dish is 24 inches in diameter and 6 inches deep, and the diameter of the cardboard cylinder is 12 inches. So this is going to be our 12 inches right there. How tall must the cylinder be to fit in the middle of the dish and be flush with the top of the dish so that it protects it? Now, the first thing that we decide is we're going to put this on the coordinate plane somewhere where it's going to be easy to do the math. And notice that we put the middle of the bottom of this dish, which is called the vertex, at 0, 0. And that means that perfectly across the top here, 12 on each side, we have their 24. So now, I want to figure out, how do I write an equation for this parabola so I can use it to figure out how tall that cylinder has to be? Now the good news is, with a little bit of thinking, we realize, well, it has to be y equals something x squared. I don't know what that something is. I'm going to use a k for that as a constant. And the reason I know that is because this parabola is opening up. So there was some number in there that makes it go up. So now I think, if I don't know what that number is, that would mean I need to know an x and a y pair that I could put in here to find k. And I have a couple of choices here. I have negative 12,6 and positive 12,6. And I'm going to stick with the positive there. Working with less negatives is always better. And we'll substitute that in. We will follow the order of operations and get 144k, and then we'll divide both sides by 144. And we'll reduce that. 6 goes into 144 24 times. So now that means my model is y equals k, which is 124, x squared. Now that I have that model, this is going to work out really nice, because what I realize is that cardboard piece that they said was 12 inches is going to have to fit right here. 6 in either direction, right in the middle. So what I can do is find this point, and I already know I'll be able to find, if not, I already do know what that point is, and you can see that, but I want to give you a chance to think about it. And then I can do a little bit of subtraction. So this top point on my box that will be the little cardboard piece there is at 6, 6. And now I want to figure out, well, how about this one? And to find that, because it's on the parabola, all I have to do is put a 6 in for x. A little reducing, and maybe as a decimal. So 1.5 is where this is. 6, comma, 1.5 is my ordered pair. So what I have to do to find the height of that cardboard is take 6 and subtract 1.5. And all of this information was given in inches. So again, we were going after the objective of, here's a graph, and let's use equations to get what we need. And so we can kind of mark that box off now. We had one that had a graph, and we went ahead and found what we needed. Multiple steps, though. You know, it's not as easy as basic as geometry and algebra 2. You have to think through all of these. Now this one says, we're going to put this under the heading forming functions from verbal descriptions, but I also see a formula down there. And again, if you've forgotten formulas, go to Appendix B. Grain is leaking through a hole in the storage bin at a constant rate of 8 cubic inches per minute. The grain forms a cone-shaped pile on the ground below. As it grows, the height of the cone always remains equal to its radius. Ooh, that sounds like a big deal. Height of the cone always remains equal to its radius. If the cone is 1 foot tall now, how tall will it be in 1 hour? Oh boy, well, we got some work to do here. All right, so first information they gave us was 8 cubic inches per minute. So I'm going to write that down as I start thinking here. If the cone is 1 foot tall now, oh, see what they're doing? They're messing with the labels. So we want to think of this as 12 inches tall right now. How tall will it be in 1 hour? Well, let's find out what it is right now. So right now, with a 12, it's going to be volume equals 1/3 pi times 12 cubed. Now, where'd that come from? Remember, they said the height and the radius are always going to be the same. So I'm just going to put those two r's together and get 1/3 pi r cubed. Now that's definitely unique to this cone. That's not always the case. They gave us that information. So now we take 12 cubed, multiply it times 1/3, and it comes out to 576 pi. So that's what it is right now, but here's the problem. There's a whole bunch of grain coming out of there at a constant rate of 8 cubic inches per minute. And it says, how tall will it be in 1 hour? Well, it's already been leaking grain for 1 hour. So let's find out how much grain. 8 cubic inches in 1 minute. And there are 60 minutes in 1 hour. And we're going to use unit analysis or dimensional analysis. The name's not particularly important here. It depends on whether or not you're doing math or science. And we're going to say the minutes will cancel out. And we'll have cubic inches in an hour. So this will come out to 480 cubic inches during that hour. So it was already at 576 pi cubic inches. And then more has leaked out. In fact, 480 cubic inches have leaked out in that hour. So the volume is now going to be 576 pi plus 480 cubic inches. All right, so an hour from now, that's how much grain is in there. And as it says, we want to know how tall it's going to be in 1 hour. Well, the radius and the height are the same. We just found out that this is going to have 576 pi plus 480 cubic inches in it, and it will be 1/3 pi r cubed. And you can make it h cubed at this point too, since we want the height. They're interchangeable because they're equal to each other. So what we would need to do is multiply both sides by 3. and get some space. That will give us 1,728 pi plus 1,440, and that's pi r cubed. Then we need to divide both sides by pi. Don't punch anything in yet. What we're trying to do is avoid a rounding error. What we want to do is punch this in as one statement and let our calculator give us the answer as exact as possible. So 1728 pi plus 1,440 divided by pi, and now we would have to take the cubed root of both sides. So pause this, go ahead and try to punch in the cubed root of, and you're going to need parentheses around that numerator since it has more than one term to get that to turn out. Should have rounded to 12.979, and that's the radius, so that is also the height. And that was in inches, because we've been talking about cubic inches all the way through the problem. So this one's interesting. You find out how much grain there is now. You think about how much grain has leaked in an hour. That gives you your new total. And then you work backwards so that you can find, well, both the radius and the height. And again, that was unique to this problem. That's not something that every cone has. Another objective marked off. Example 5, letting units work for you. So this one, as I mentioned before, unit analysis and dimensional analysis is what we're going to have to do here. And this is really verbal descriptions. It is what's taking place here. Yes, we are going to use some formulas in here too, so this is kind of a mixture. So it says, how many rotations does a 15-inch radius tire make per second on a sport utility vehicle that's traveling 70 miles per hour? I'm going to start with that 70 miles per hour, because here's what I noticed. They were asking us about rotations per second. So I don't want to keep that in hours. I want to work that towards seconds. So we start thinking, well, in 1 hour, there are 60 minutes. Still not seconds. So I'm going to need in 1 minute, there are 60 seconds. And now minutes would cancel for my labels and hours would cancel, and I'd be left with miles per second. That's not what I need. I need rotations per second. So the second part is done. But now I need to figure out how to put something with rotations on the top. And I realize, well, each rotation, I know how far it's gone because that's circumference. And circumference is 2 pi r. So there's that part of our objective where we're using formulas. So that's going to give me 30 pi. So one rotation is going to be 30 pi, and this was in inches. And now I realize I have my rotation, and on the bottom, I have too many labels. So what I need to get rid of is the miles and inches, which is a good thing because we know all kinds of things about that. So we know that in 1 mile, I need the miles on the bottom, so it will cancel with miles on the top back here. There is 5,280 feet. And I know that in 1 foot, there are 12 inches. So now let's go back. I'm going to put a big equals here. But let's go back and actually put a strike through those labels so that we'll see that unit analysis, dimensional analysis work. Hours will be gone. Minutes will be gone. Seconds has to stay. This was inches, miles with miles. Inches with inches, feet with feet. And as I look at the labels, I see the only label that's left on the top is rotation. And the only label that's left on the bottom is second. So one of the dangers here, it happens quite a bit in fact, is that people forget to punch in the pi down here. So don't be one of the people that forget that. But remember, fractions are top times top times top times top times top all the way through, divided by bottom times bottom times bottom times bottom times bottom times bottom. And again, punch this in and let's see if everybody can get the same thing. 13.072 rotations per second is what you should get. And again, most missed part to that is the pi piece on the bottom. So make sure you use your actual pi button on your calculator, which is that second caret symbol. Now, forming functions from data. That's part of our objective we haven't talked about yet. So we've got another chunk of info here, and it says constructing a function from data, given a set of data points of the form ordered pairs x, y, to construct a formula that approximates y as a function of x. Make a scatter plot of the data points. Always a good idea. The points do not need to pass the vertical line test. It doesn't have to be a function. Determine from the shape of the plot whether the points seem to follow the graph of a familiar type of function. So does it look like one of our 12 basic functions as you go through it? Lines, parabolas, cubics, sine curves, etc. Transform a basic function of that type to fit the points as closely as possible. That means we're going to use the graphing calculator, because the graphing calculator uses a process called least squares regression, and it's more accurate than we could ever get by hand. So example 6 says curve fitting with technology. And this table has low and high daily temperatures that were observed from September 9th, 1999 in 20 major American cities. Find a function that approximates the high temperature y as a function of the low temperature x. Use this function to predict the high temperature that day for Madison, Wisconsin, given that the low was 46 degrees. Now, I need you to take the time to put the lows in to list 1, and there are 2 columns of these. Every year somebody forgets and only puts 1 in. And then go back into list 2 and put the 2 columns of highs into list 2. And you can go ahead and pause because I cheated and I put these in my calculator already. So hit pause and get those in. All right. So at this point, what we would want to do is look at the scatter plot, and you can see the book gave it to us, but we would want to see the scatter plot to be sure. So I'm going to go in and get rid of what I had in there before, and I'm going to change my window so I'm able to see all of these high and low temperatures here. And so the lows, I'll just go from 0 to, I'll just do 0 to 100, make it easier. And my highs, 0 to 120. Oh, second stat plot. So second y equals. I've got to turn one of those on. Number 1, I want it on, so I hit enter. And it is list 1 and list 2, and blue is a perfectly fine color. Graph. So there it is. Now, it looks like we should be able to get a pretty good line of best fit out of that. So the next thing I need to do is make sure that I have my diagnostics turned on my calculator so that I will be seeing a correlation coefficient. To do that, we hit second 0, that gives us the catalog. And I'm going to go down until I see diagnostics on. And I have to hit enter twice. I have to select it, and then I have to execute it. So now my diagnostics are on. Next step is going to be to do the linear regression. So we hit stats, and arrow to the right once to calculate. Number 4 is linear regression. And I do want to store this. I want to see exactly where it is in relation to all of the points I have in my stat plot. So variables, V-A-R-S, Y variables, hitting the arrow once to the right. Number 1 for functions and number 1 for y sub 1. All the way down to calculate, and there it is. So there is our line of best fit. Y equals 0.970x plus 23.015. But while I'm here, I will look at that R value, that correlation coefficient. 0.899 to 2 decimal places. And remember, the closer that is to 1, the better the line of best fit. This is a pretty good one. That's a pretty high value that we have there for our correlation coefficient. So we go back to the page and we write down that we chose linear regression. And we take a quick peek to see, did they say that we were writing a function? Yep, it says find a function. So we have to name this something with function notation. Use this function to predict the high temperature that day for Madison, Wisconsin, given that the low was 46. Well, our x's were the lows. So what we would need to do is put a 46 in for x and then crank that out on the calculator, or we can go to the table feature, second window table set, and we can start it at 46 and then hit second graph and see that it's 67.63. But we'd realize, oh, we're missing a decimal place. I need the third decimal place. So we'd end up punching it into the calculator anyway and getting f of 46, which would be 67.635 degrees. So we made a model there from data. That's what linear regression is using the data to get ourselves a nice model. And since it all lined up very nicely for linear regression, that's what we did. Now, like it says, keep this data and equation in your calculator. You'll need it again. And that's because it says professional statisticians would be quick to point out that this function should not be trusted as a model for all cities, despite the fairly successful prediction for Madison, Wisconsin. For example, the prediction for San Francisco, with a low of 54 and a high of 64, is off by more than 11 degrees. The effectiveness of a database model is highly dependent on the number of data points and on the way they were selected. The more data you have, the better. The functions we construct from data in this book should be analyzed for how well they model the data, not for how well they model the larger population from which the data came. Yeah, use it to talk about what you see in the data itself. Now, if you go under stats and calculate, you'll see there's all types of regression there. We have linear, we have quadratic, we have cubic, we have quartic, we have natural logarithm regression, exponential regression, and two different types here. Power regression, logistic regression, and then using the sine curve, sinusoidal regression. So these can model pretty close to anything. You know, we can get super close using these regression models. And of course, if you use these all the time at an office or whatever work it is you're doing, they probably have software to generate those curves. Now, these graphs are only examples, as they can vary in shape and orientation. For example, any of the curves could appear upside down. The grapher uses various strategies to fit these curves to the data, most of them based on combining function composition with linear regression. Depending on the regression type, the grapher may display a number, lowercase r, called the correlation coefficient, or a number r squared, it could be capital R squared, and that's called the coefficient of determination. In either case, a useful rule of thumb is that the closer the absolute value of this number is to 1, the better the curve fits the data. Yeah. So don't worry about a plus or minus. Don't worry about the negative or positive value. Worry about the number itself. Is it close to 1? If it's close to 1, then it's a really good fit. So look back at the temperature data and the linear regression equation that we found. What is that correlation coefficient? Well, R was approximately 0.899, which, rounding to the nearest tenth, would be 0.9. So it has a fairly strong correlation to the data. At that 0.9 piece. And then what does this tell us? Well, this is a pretty good line of best fit. It's not perfect. It didn't come out to be 1, but it was a pretty good model for the situation that we had. Now, like it says, note, if you don't have an R value, how we got that was by doing second 0 in the catalog, and then we scrolled down to diagnostics on. And you have to make sure that you hit enter twice so that you see the word done. We have to execute it. So that met all of our objectives. We had written functions from formulas, graphs, verbal descriptions, and data in little chunks of problems here, some of them using 2 of those at one time. So there is the homework for this section. which of course will mix and match all of those models, just like we saw as we went through today's notes. Section 1.7.